In the last video, we started discussing the rate law, and we are going to continue that here in this video, talking about how we can tell if something is first order, second order, or zero order. And we're going to do some practice problems with what we call the integrated rate law as well. But before we get into all that, just to kind of remind you of the rate law and what we discussed in the last video here. This is the generic form of the rate law. If we have two things there, we don't have to have two. We could have this as well. It could just be one thing in the rate law. It doesn't have to be two, and it can be more than two. As we can see, there's actually one situation where we don't even have anything here. There's no concentration. So there's a few different forms, but usually we'll have one or two things, one or two concentrations in the rate law. And so the rate law is the rate is equal to the rate constant, which is K, times the concentration of a reactant raised to some coefficient. If we're looking at this equation and we're doing multiple experiments, and we notice that when we double the concentration of A and the rate doubles, what that tells us is that the order with respect to A is 1. I know it might seem for a second like saying, well, wait a second, you just said that it doubled. Wouldn't that mean that it's second order if it doubled? And no, actually, because we're seeing the same change in the concentration that we see with the rate, that is first order. You could think about it in terms of, like if we had something like this, where we had the rate is equal to, we'll say 1, and actually let me just rewrite this. So this is the rate here. The rate is 1, and it's 1 when we have some K value times a concentration of 1 raised to the 1. So this is I'm just putting random numbers here, not truly random. I'm picking easy numbers to work with. But if we have a concentration of 1, and we're pretending like K is also 1 in this case, and it's raised to the order of the 1, then the rate ends up being 1. If I double the concentration, so this is the rate here, if I double the concentration while keeping everything else the same, then the rate is going to end up being 2. The rate is going to double. If, on the other hand, this exponent was not 1, if the exponent was 2, I wouldn't end up with a rate of 2. I would end up with a rate of 4, because I would be raising this concentration to the second power, and so I wouldn't just end up with the same change. It increases the change there, which then answers this next question here. If we doubled the concentration of B and the rate increased by a factor of 4, that would mean that it is second order with respect to B. So if we make a change in the concentration and we see the same change in the rate, that means that we have first order with respect to that reactant. If we make some change in a reactant and we see a doubling of that change, then that means that we have second order. So essentially, whatever change we see raised to the second power. I really shouldn't say doubling. That's not actually mathematically correct. That's just, in this case, 2 squared is the same as 2 times 2. But if we see a squaring of the change, then that means that we have second order with respect to that particular reactant. The last one here, if a reaction is zero order with respect to A, what happens when we triple the concentration of A? Well, let's think about this. If we have our rate law, and we have some k value. We actually don't really care what k is at this point. And we have, in one case, 1 as the concentration, but in the other case, 3. We've tripled it from 1 to 3 for the concentration, but it's 0 order. What is 3 raised to the 0? If you remember your high school algebra, you'll remember that anything raised to the 0 is 1. Doesn't matter what it is. Doesn't matter how much you increase it or how much you decrease it. It's still 1. And so 0 order reactions, actually I can write the rate law for every 0 order reaction in existence right now. There it is. The rate is just equal to k. The rate is just equal to the rate constant. Now, technically, there is other stuff here. There's some molecule here as well, but we just ignore it because it's raised to the 0, which just makes it 1. But technically, chemically speaking, we still need this here. There still has to be some concentration of the reactants for the reaction to occur at all. So if we have 0 of the reactant, well then obviously the reaction can't occur. But as long as there is some amount, as long as there's some non-zero amount of reactant present, the rate will not change at all based on that amount. It is only based on k. And so the reaction will just keep on going until it uses up all of the reactants, at which point it's 0. All right, let's look at an example problem here. So this says, consider the reaction between nitrogen dioxide and carbon monoxide. The initial rate of the reaction is measured at several different concentrations of the reactant with the accompanied results. From the data, determine the rate law for the reaction and the rate constant for the reaction. So what we're going to do here is very similar to what we did in the last video, where we had this big set of data. We need to find 2 experiments where one of the reactants is held constant and the other one changes, and then 2 experiments where the other reactant is held constant and the other is changing. So for example here, these first 2. The CO is held constant, but the NO2 is changing. What this is going to allow us to find are the M and N values here, because we need to figure out what is the order with respect to each of these things. So if we look at this first 2 here, CO is held constant, which means any change we see in the rate is due to NO2. And if we look at NO2, its concentration doubles. The rate essentially quadruples. Now it is a little bit off, but that is very typical. No data is perfect. If you have perfect data, that means someone made it up. Someone created it. If you actually go out and collect data yourself, it's never going to be absolutely perfect. So even though this isn't exactly quadrupled, it is essentially quadrupled, which means that N is 2. Because remember, again, if we double the concentration and the rate quadruples, essentially what we've done there is we've taken the doubling and we've squared it, which gives us 4 times the change. For the other ones, we do not want to take these 2, the bottom 2. It might seem like that at first because, hey, look, those 2 are changing. But these 2 are also changing. And it's going to muddy up the waters. We don't want that. So instead, we're going to take these 2, the second one and the third one. And with these 2, the NO2 stays constant, so any change we see in the rate is only due to CO. And if we look at the rate, it technically does change, but it's practically the same, which means m is 0. If we see essentially no change in the rate when we double the carbon monoxide, that means that the carbon monoxide is not having an effect on the rate. Now again, I want to stress, I am not saying that the carbon monoxide is not participating in the reaction. It has to be there, but it's not having an effect on the rate. Okay, so then we know N and M, so we can write the rate law. We had it nearly written before, we just didn't have those coefficients. So this is going to be 0, this is going to be 2, and truthfully, this is not the normal way you would write this. Normally, you would leave out the 0 order. So it would just be that. Again, technically the CO does have to be there, but it's not having an effect on the rate. So then the last part here, find the rate constant for the reaction. And if you're thinking, how are we supposed to find the rate constant? I didn't see anything about the rate constant anywhere. Well, check out that equation we just wrote. It has the rate constant in it. Not only that, the rate and the concentration of NO2, we have a bunch of those. So what we're going to do is we're just going to pick one of these. Actually, it doesn't matter which one. Might as well just do the first one. So we're going to take this concentration, this rate, plug them in, and solve for K. So the rate, 0.0021 molar per second, is equal to K times 0.1 squared. And let's see here, let me do that math. K is 0.21, and let's see, that was molar, so it's going to be 1 over molar seconds. Alright. I hope that made sense. If not, feel free to rewind and go over it 1 or 2 more times. I was going to do the integrated rate laws on this video, but I think I'm actually going to leave that and do it in its own video. Otherwise, this will turn into a 25-minute long video. So we'll call it there for this one, and then the next one, we will finally talk about the integrated rate law.